Welcome to the Deep Dive. Today we're going to tackle a moment in history that is, well, arguably one of the most important transformations ever.
It's a huge claim, isn't it?
It is. We're talking about the scientific revolution. And it's not just about a few new discoveries, it's about the moment humanity decided to fundamentally rewrite the entire rule book for how we know what we know.
I think it's the perfect way to frame it. You know, people often compare it to the Neolithic Revolution.
Right, when we learned how to farm.
Exactly. And that changed how we lived, how we sustained ourselves. But the scientific revolution changed how we understood reality itself. It was a change in the mind.
So our mission today in this deep dive is to really get under the hood of that shift. Not just what was discovered, but how the whole process of acquiring knowledge was, well, reinvented.
A total reinvention. And it happened primarily in Western Europe over a pretty specific span of time.
Okay, so let's put some guardrails on that. When historians talk about this period, where do they draw the start and end lines?
Well, the traditional dating bookends the whole era with two monumental sets of publications. It kicks off in 1543.
1543, and what happened that year?
You get two foundational texts published almost simultaneously that challenge the old order in completely different fields. It's an amazing coincidence, really.
Okay, lay them on us.
On the one hand, you have Andreas Vesalius, who publishes the Humani Corporis Fabrica,
Which is?
on the workings of the human body. And it was a direct, visual, and frankly, brutal assault on 2,000 years of medical authority held by the ancient physician Galen.
So that's the revolution in understanding ourselves, our bodies. What was the other one?
The other was Nicholas Copernicus's De Revolutionibus, on the revolutions of the heavenly spheres.
The big one? The one that moved the
The one that moved the Earth. It proposed a sun-centered system which flew in the face of, well, all of Western cosmology going back to the Greeks. So you have the microcosm and the macrocosm both being turned upside down in the same year.
An incredible starting point. So if 1543 is the disruptive beginning, where's the finish line? What's the grand finale?
The culmination, the great synthesis, arrives in 1687.
Wait,
Isaac Newton's Philosophiae Naturalis Principia Mathematica, the Principia.
of course.
And when you frame the era between Copernicus and Newton, you're defining a period that saw this irreversible break with what came before, with natural philosophy.
So the new science, as they called it, what made it so new?
It was more mechanistic. It was deeply, fundamentally integrated with mathematics in a way that had never happened before. And maybe most importantly, it was completely dependent on gathering new empirical evidence.
So high level, what was the significance of all this? What really changed in the big picture?
I mean, science as we know it was born. It became its own thing, an autonomous discipline, separate from philosophy on one side and just, tinkering or technology on the other.
It started to have a purpose.
A utilitarian purpose. Suddenly, the goal of science wasn't just to contemplate the heavens. It was to solve human problems, to make life better. The rapid, accelerating accumulation of knowledge that defines our modern world. It all starts right here.
To really get a feel for what a revolution this was, we have to start with what was being overthrown, the intellectual foundation of Europe for centuries.
The Aristotelian tradition. I mean, it's hard to overstate how completely it dominated every facet of intellectual life.
It was more than just a model of the planets. It was a complete philosophy of reality.
A complete, coherent, and deeply intuitive one. It placed the Earth, our world, right at the center of everything. But it wasn't just a physical model. It was a philosophical one that divided reality into two totally separate realms.
Okay, let's start with our realm, the one we live in, the terrestrial region. You said it was imperfect.
Imperfect is the realm of change, of decay, of generation, and corruption. Everything here was made of the four classical elements.
Earth, water, air, and fire.
Right. And every single object in this realm had a natural movement, a tendency to go to its natural place.
So a rock, which is made of earth, naturally wants to go down.
Down toward the center of the universe, which was the center of the Earth. Water also moved down. Air and fire, being lighter, their natural movement was up, away from the center.
So if I throw that rock, I'm forcing it to do something it doesn't want to do.
Exactly. That's called violent motion. It's temporary, it's forced, and it requires a continuous external push. The second you start pushing, its natural tendency to just fall takes over again. It was all about purpose, about teleology.
But then you look up past the moon, and the rules of physics just change.
Completely. You've entered the celestial region, the realm of the perfect. It was eternal, it was unchanging.
And wasn't made of earth, water, air, or fire.
No, it was made of a fifth element, the ether. And because this realm was perfect, its motion had to be perfect. And the only perfect motion was
Uniform circular motion.
uniform circular motion. The heavens were a series of nested, crystalline spheres, all rotating eternally and perfectly around the central Earth. This sharp, absolute distinction between the messy, straight-line motions on Earth and the perfect circular motions in the heavens, that was the bedrock.
But there was a problem. The planets don't always move in perfect circles from our perspective. Sometimes they seem to slow down, stop, and even go backward.
Retrograde motion.
Yeah.
And that was a computational nightmare for the pure sphere model.
And that's where Ptolemy comes in, right? Trying to fix the math.
Claudius Ptolemy's Almagest is this monumental work of ancient science, where he formalizes the geometric tricks you need to make the geocentric model actually work, to make it predictive.
Tricks like epicycles.
Epicycles, difference, eccentrics. I mean, it gets incredibly complicated.
Can you break that down? What are we actually picturing here?
Okay, so imagine the main circle a planet takes around the Earth. That's the different. But the planet isn't actually on that circle. It's on a smaller circle, the epicycle, that is itself rolling along the edge of the bigger circle.
So it's a circle on a circle. It sounds like one of those spirograph toys.
That's a fantastic analogy. It is. And to make the predictions even more accurate, the center of the main circle, the deferent, might not even be the Earth. It might be offset slightly. That's an eccentric.
So you're layering all these geometric fixes on top of each other.
You are, all to preserve two things: the central Earth and uniform circular motion. The math was brilliant, it worked for predictions, but the physical reality of it was getting, well, very strained by the 16th century.
That sets the stage perfectly. But revelations don't happen in a vacuum. You need technology, you need infrastructure, and the key enabler for this entire scientific awakening was invented about a century before Copernicus.
The printing press.
The printing press.
It's almost impossible for us to grasp the impact. It changed everything about how knowledge was created, shared, and validated. Before the 1440s, there was no mass market for a scientific book. Religious texts, sure, but not science.
And if you were trying to copy a book by hand, especially one with diagrams,
You'd get errors. Scribal errors, misinterpretations, things left out. The errors would compound with every new copy. But printing allowed for the accurate mass reproduction of everything: text, maps, and crucially anatomical drawings.
so it wasn't just about making knowledge cheaper, it was about making it consistent, standardized.
Absolutely. A researcher in Padua could be looking at the exact same edition of a text by Archimedes as a scholar in London. They could compare their own new observations to a stable, reliable foundation. You didn't have to, as one source put it, always start from scratch.
And for a science like anatomy, the visual accuracy must have been a revolution in itself.
A total revolution. They moved from woodcuts, which were okay but would wear down and lose detail with every printing,
To what?
to engraved metal plates. These allowed for incredibly precise, high-fidelity images that could be reproduced thousands of times without decaying. Permanent visual information.
But even with this new tech, mistakes could still happen. I read that Galileo's first big publication had some issues.
That's a wonderful detail. When Galileo published his Sidereus Nuncius in 1610, with those stunning first telescopic drawings of the moon,
The ones that showed it had mountains and craters, that it wasn't a perfect sphere.
those ones, in the very first printing, the images of the moon came out back to front. A printing blunder. It just underscores that even the most revolutionary content depended on a manufacturing chain that was still, figuring things out.
Now, we've set this up as a great break, but you also mentioned that a lot of these pioneers were actually very respectful of the ancients. It wasn't a total rejection.
And this is the core of what historians call the continuity thesis. It's not as simple as Aristotle bad, Newton good, figures like Copernicus, Galileo, Kepler, even Newton himself. They were meticulous about tracing ancient and medieval pedigrees for their big ideas.
They were trying to show they weren't just making things up out of thin air.
Precisely. They were often reviving minority views from antiquity that had been suppressed by the dominant Aristotelian framework.
Can you give us an example of that?
The heliocentric system itself. Copernicus knew perfectly well that Aristarchus of Samos had proposed a sun-centered system back in the 3rd century BC.
So he was bringing back an old idea, not inventing a new one.
He was giving it a rigorous mathematical framework it never had before. Same with Newton. When he laid out his laws of motion, he traced the concept of inertia, the idea that a body in motion stays in motion, all the way back to ancient atomists.
And he even credited his contemporaries in the Principia, didn't he?
He did. He makes a point of saying that his three laws of motion were already accepted by guys like Christian Huygens and Christopher Wren. He saw his work as the grand mathematical formalization of ideas that had been sort of floating around for a long time. The systematic rigor, though, that was new. That was the revolution.
Okay, so if the core ideas had some ancient roots, then the real revolution has to be in the process, the method. This move from the book-reading philosopher to the hands-on experimentalist.
That's it exactly. The shift in approach was just profound. Under the old Aristotelian model, observation was passive. You'd go out and look for natural circumstances.
So you're just confirming what you already believe.
You're confirming the essence of a thing. If you saw a weird plant, a mutation, you'd dismiss it. It's an aberration, an imperfection that tells you nothing about plantness.
But the new way of thinking flipped that completely.
It said, we don't wait for nature to show us its secrets. We have to design experiments to force it to reveal them. We have to manipulate it, put it under stress, and this put empirical evidence, the result you can see and measure, right at the center of everything.
John Locke really formalized the philosophy behind this a little later on, didn't he?
He did. In his essay concerning human understanding in 1689, he gives us the idea of the tabula rasa.
The blank slate.
The blank slate. The mind has no innate ideas.
Mm.
All true knowledge comes from experience. Sensory impressions get written on that tablet, and then our minds reflect on them to build up knowledge. It's a foundational idea for empiricism.
So if Locke built the philosophical house, Francis Bacon drew up the blueprints for the method, the father of empiricism.
Bacon's ambition was just staggering. He wanted a complete reformation of all knowledge, what he called the Instauratio Magna, the Great Instauration.
And his goal was explicitly practical.
Utterly practical. To advance learning in order to relieve mankind's miseries. He had these two central maxims. First, man is the minister and interpreter of nature.
Okay.
And second, and this is the crucial one, nature can only be commanded by obeying her.
You have to understand the rules before you can use them.
You have to submit to the evidence first. It's a complete inversion of the old way, where you started with the philosophical principle and tried to make the evidence fit.
And he proposed a whole new system of logic to replace the old scholastic methods.
Right. He attacked the syllogism, which argues from general premises down to specifics. Bacon wanted to go the other way.
Inductive reasoning.
Inductive reasoning. You start with specific, carefully gathered facts, and from there you move upward to axioms or theories, and finally to general physical laws. And you do it through what he called eliminative induction.
Meaning you test all the possibilities and eliminate the ones that don't work.
Exactly. You systematically rule out hypotheses until only the correct one remains.
And he was very focused on all the ways our own minds can trick us.
Oh, absolutely. He talked about the idols of the mind, these false notions and biases we all have that get in the way of seeing things clearly. He was particularly critical of traditional philosophy, saying it was too obsessed with words and debate. It made science, in his words, sophistical and inactive.
He wanted results, inventions.
Yes.
Yeah.
For him, the whole point of science was to better human life by producing new inventions, which he saw as new creations and imitations of divine works. It gave science a kind of moral purpose.
It's important to remember, though, that for all his genius about the method, he wasn't always right about the science of his own day.
That's a fantastic point. He was a visionary for the process, but he actually rejected a lot of correct theories. He dismissed Copernicus's heliocentrism, Kepler's laws, even William Gilbert's work on magnetism.
So Bacon gives us the theory of the scientific method.
Yeah.
How did people actually start putting it into practice?
Well, Bacon's description is great. He said you first have to light the candle. That's your hypothesis. And then you use the candle to show the way, which means designing your experiment to test it. And that's exactly what you see in the work of pioneers like William Gilbert.
Gilbert published De Magnete in 1600, even before Bacon's big work. He was a true experimentalist.
A passionate one. He hated Aristotelianism. He famously built a model Earth, a spherical magnet he called a terrella.
A little Earth.
A little Earth. And he used tiny compasses and needles to meticulously map its magnetic field. And from these experiments, he concluded that the Earth itself must be a giant magnet, and that's why compasses point north. The rigor of how he described his experiments was hugely influential.
But the figure who really brings it all together, the experiment and the math, is Galileo.
Galileo's the one. He makes a decisive, world-changing claim. The laws of nature are mathematical.
The book of nature is written in the language of mathematics.
That's the quote. He said the universe cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written, triangles, circles, and other geometrical figures.
It's such a profound statement. It's saying reality has a mathematical structure.
An objective structure. He even said that when it comes to the certainty of mathematical propositions, human knowledge equals the divine.
Wow.
And to make that work, his experiments had to be precise. He needed standardized measurements of time and distance, things we take for granted, so he could make reproducible comparisons and confirm his mathematical laws.
And once that door was opened, this idea of mathematizing nature just exploded.
It did. But it required new mathematical tools. You get Francois Viet introducing symbolic notation to algebra in 1591, which makes it so much more powerful. You get Descartes in 1637 linking algebra and geometry with Cartesian coordinates.
And then the ultimate tool for describing a world in motion.
Newton's development of infinitesimal calculus,
Yeah.
it just opened up vast new territories for analysis. The universe wasn't just observable anymore, it was quantifiable.
All of this, the focus on parts, on motion, on math, it coalesces into a new worldview, the mechanical philosophy.
Right, and this was the final death blow to Aristotle's teleology. The old view had four causes, but the most important was the final cause, the purpose.
Why a thing exists.
Why it exists, what its goal is. The mechanical philosophy just strips all of that away. The universe is not an organism with purposes, it's a machine, a giant clockwork.
And its parts are just inert particles.
Inert particles or corpuscles. They have no goals, no desires, they just move. And the only way they move is by being hit by other particles.
Yeah.
Direct physical collision, like billiard balls.
So no mysterious forces, no action at a distance.
Absolutely not. That was seen as a throwback to magic and mysticism. Which brings us to the great paradox of the whole revolution.
Isaac Newton.
Isaac Newton. Because when he introduces his theory of universal gravitation, what is it?
It's an invisible force acting instantaneously across the vast emptiness of space. It's spooky action at a distance.
It's the very thing the mechanical philosophy was supposed to eliminate. And his critics jumped all over it, calling it an occult quality, a hidden magical power.
How did Newton deal with that?
Very cautiously.
Yeah.
It's where his famous phrase, hypotheses non fingo, comes from. I frame no hypotheses.
Meaning he wasn't going to guess why gravity worked.
Exactly. He said, look, the math works. The phenomena prove that this force of attraction exists. That's enough.
Yeah.
I don't need a mechanical explanation for its cause.
But that wasn't a very satisfying position for people.
Not at all. And it was actually his collaborator, Roger Coates, who provided the philosophical out. In the preface to the second edition of the Principia, Coates argued that gravity was just another inherent power of matter given to it by God, just like inertia was.
So it's just a fundamental property of the universe.
It's just a rule of the game. And by the mid-18th century, that view was totally accepted. It paved the way for all of modern physics, which is full of field forces and action at a distance.
Okay, so we have the method, the math, the worldview. But for this to stick, for it to become permanent, it needed to be institutionalized.
This is maybe the most important part. Knowledge needed a home. And the first one was the Royal Society of London, founded in 1660.
It grew out of these informal meetings of natural philosophers, right?
At a place called Gresham College. And they were hugely inspired by Francis Bacon's vision of a cooperative research institute. They even got a royal charter from King Charles II.
To be a college for the promoting of physico-mathematical experimental learning?
A bit of a mouthful, but says it all. And they appointed a curator of experiments, Robert Hooke, whose job was to perform experiments at every meeting.
What were those early meetings like?
A real mix. Sometimes you'd have incredibly important experiments, like Robert Boyle demonstrating his vacuum pump. Other times, it was, much more trivial stuff. But the spirit was always hands-on, observational, and about collective vetting of knowledge.
And their single greatest contribution to the future of science
Has to be their journal, Philosophical Transactions, which started in 1665.
the first scientific journal?
The world's oldest and longest running. And it established two principles that are still the bedrock of science today. Scientific priority, who gets the credit, and peer review. It created the formal system for sharing and validating new knowledge.
And the French followed suit soon after.
The French Academy of Sciences was founded in 1666, but it was a very different beast. It wasn't a private club of gentlemen scholars like the Royal Society.
It was a government body.
It was an organ of the state, founded by the King's minister, Jean-Baptiste Colbert. It had state funding, salaries for its members, and was often focused on problems of national importance, like map-making or improving navigation.
So let's turn from the method to the actual discoveries, starting with a big one, astronomy, the displacement of Earth from the center of everything.
It was just a conceptual earthquake.
Yeah.
For millennia, the Earth was the stable, unmoving foundation of reality. The idea that it was just another planet hurtling through space was, well, deeply unsettling.
It completely destroyed that neat division between the perfect heavens and the imperfect Earth.
It had to. If the Earth moves, then it must be made of the same stuff as the planets. And if the planets are like the Earth, they must be changeable, imperfect. The whole Aristotelian cosmos just crumbles.
But it took a while for Copernicus's idea to really catch on. What was the big objection people raised?
The lack of observable stellar parallax.
Can you explain that?
Sure. If the Earth is orbiting the Sun, then our viewing position changes dramatically over 6 months. So the nearest stars should seem to shift their position slightly against the background of more distant stars.
Like when you hold your thumb out and close one eye, then the other, your thumb seems to jump.
That's the perfect analogy. They looked for that shift, and with the instruments they had, they couldn't see it. So for decades, many people thought Copernicus's system was just a useful mathematical trick, not a description of physical reality.
Then comes Johannes Kepler, with access to the best data in the world.
Tycho Brahe's data. Incredibly precise, naked-eye observations made over decades. And Kepler, who was a mathematical genius, spends years trying to make the data for Mars fit a circular orbit.
And it just won't work.
It's off by a tiny amount, but it's enough. So he makes this incredible intellectual leap and tries an ellipse. And it fits perfectly.
So planets move in ellipses, not circles.
Which was a death blow to the old cosmology. The heavens were not perfect. Planets were just bodies moving according to physical laws. His book, Astronomia Nova, is one of the most important works of the whole revolution.
And then Galileo comes along and provides the killer observational evidence with his telescope.
He weaponized it for astronomy. Every single thing he saw through it was another nail in the coffin of the Ptolemaic system.
The moons of Jupiter.
Right. If Jupiter has moons, then not everything orbits the Earth.
The phases of Venus.
That was the big one. He saw that Venus goes through a full set of phases, just like our moon. That's only physically possible if Venus orbits the sun, not the Earth.
And the mountains on the moon and spots on the sun.
Exactly. They proved that celestial bodies were not perfect, unchanging ethereal spheres. They were worlds, just like ours, blemished and changeable.
But there is still that common sense objection. If the Earth is spinning and flying through space, why don't we all just fly off? Why does a rock drop from a tower land at its base?
And Galileo had a brilliant answer for that, a preliminary theory of inertia. He argued that the rock, the tower, and the person dropping it are all already moving together with the Earth.
So the rock doesn't lose that sideways motion just because you let it go?
It retains it. It's just adding a downward motion to the horizontal motion it already had. It's a revolutionary concept that dismantled the last major argument against a moving Earth.
And Newton, with the Principia, delivers the final synthesis.
He unifies the whole thing. His laws of motion and universal gravitation show that the force that makes an apple fall to the Earth is the very same force that keeps the moon in orbit around the Earth and the planets in orbit around the sun.
One set of laws for the entire universe.
The end of the two realms. The cosmos was a single unified machine governed by universal mathematical principles. And with that, the heliocentric model was no longer in doubt.
Following that idea of the machine, let's shift from the cosmos to the body, to biology and medicine, where the authority of Galen was just as absolute as Aristotle's.
For more than 1,000 years, if you were a physician in Europe, the works of Galen were your Bible. But Galen had a problem.
He wasn't dissecting humans.
He was working in the Roman Empire, where human dissection was forbidden. So his anatomy was based largely on dissecting animals, pigs, Barbary apes.
And Vesalius, in 1543, changes that.
He breaks the taboo. He performs human dissections, and his book, De Humani Corporis Fabrica, is filled with incredibly detailed and accurate drawings based on what he actually saw. And what he saw often contradicted Galen.
So he was promoting an empirical, observational view of the body.
Exactly. The body as a physical structure in three-dimensional space that had to be seen and mapped, not just read about in an ancient text.
What were some of the specific errors he corrected?
Big one was in the heart. Galen believed there were tiny pores in the septum, the wall between the two main chambers, allowing blood to seep from one side to the other.
Based on what he saw in pigs.
Right. Vesalius looked at human hearts and said, no. The septum is solid. There are no pores. Which raised a huge question about how blood actually moved. He also gave us the first good descriptions of all sorts of bones and organs and the best anatomy of the brain up to that point.
So Vesalius gives us the structure, then William Harvey gives us the function.
Harvey gives us physiology. His 1628 book, De Motu Cordis on the Motion of the Heart, is a masterpiece of the new scientific method. It combines careful experiment with elegant mathematical deduction.
How did he use math to attack the old theory of blood?
Well, the Galenic theory was that the liver constantly made new blood from the food we eat, and the body then consumed it like fuel.
Okay.
So Harvey did a simple calculation. He measured how much blood the heart's ventricles could hold. He multiplied that by the number of heartbeats in an hour, and the result was just, well, absurd.
What did he find?
He found that for the Galenic theory to be true, the liver would have to produce something like 540 pounds of blood every single day, an impossible amount. The sheer math showed the old theory had to be wrong.
So what was his alternative?
That the blood circulates. It's a closed system. The heart is a pump that drives the same blood around and around the body.
And he proved this with experiments.
Simple, elegant experiments. He would tie ligatures or tight bands on people's arms. A very tight band would cut off all flow and the arm would go cold and pale. But if he loosened it just a little, enough to let arterial blood in but block the veins from taking it back out,
The arm would swell up.
it would get warm and red, and the veins below the ligature would bulge with trapped blood. It was undeniable proof of a one-way circular flow.
Beyond these two giants, you see a lot of specialization starting to happen in medicine.
You do. A physician named Jean Fresnel coins the term physiology to describe this new study of bodily function. You have Pierre Fauchard basically inventing modern dentistry, and Ambroise Paré revolutionizing surgery, especially on the battlefield.
Now let's move to chemistry, which had to fight its way out of the shadow of its mystical twin, alchemy.
They were very deeply entangled. I mean, hugely important figures like Tycho Brahe and even Isaac Newton were serious alchemists. And chemical philosophy, unlike mechanical philosophy, often talked about the active powers in matter, vital principles, spirits.
But the shift toward a more practical, less mystical approach started in industry.
It started with mining and metallurgy. A 1556 book, De Re Metallica by Georges Agricola, was hugely important. It was a practical manual describing in meticulous detail the processes of mining and extracting metals. It stripped away the mysticism.
But the figure who really defines the break, who is called the first modern chemist, is Robert Boyle.
Boyle's the one who systematically applies the new scientific method to chemistry. His book from 1661, The Skeptical Chemist, is a direct assault on the old alchemical ideas.
What was his main argument?
He argued from the mechanical philosophy. Chemical reactions weren't caused by mystical sympathies or active spirits. They were the result of the physical collisions of particles in motion.
And he wanted chemistry to stand on its own 2 feet.
Yes. He pleaded for it to stop being just a handmaiden to medicine or a search for the philosopher's stone. He said it should be a science in its own right, and that every single theory had to be proven experimentally.
And he backed that up with one of the first great quantitative laws in chemistry.
Boyle's law from 1662. The inverse relationship between the pressure and volume of a gas. It's a simple mathematical equation. P times V equals a constant. It proved that chemistry could be just as mathematical and rigorous as physics.
Finally, in this section, let's look at the physical sciences, especially optics and electricity.
Optics made huge strides. Kepler, again, founded modern optics in 1604, figuring out things like the inverse square law for light intensity. And Willibald Snellius discovers the law of refraction.
And then Newton comes in and completely changes our understanding of color itself.
His experiments with prisms are just legendary. He showed that a prism doesn't create color. It separates or decomposes white light into the spectrum of colors it already contains.
And a second prism could put them back together into white light.
Right, which led to his revolutionary theory that color isn't a property of objects, it's a property of light. Objects just reflect or absorb certain colors that are already present in the light hitting them. He laid this all out in his book, Optics.
And the practical side of optics, the microscope, opened up a whole new universe.
While Galileo was looking up at the stars, Antony van Leeuwenhoek was looking down at a drop of pond water. He built these incredibly powerful single-lens microscopes and was the first human to see bacteria, blood cells, all sorts of microscopic life. He essentially founded the field of microbiology.
And what about electricity? William Gilbert, the magnetism guy, shows up here again.
He's the founder of the electrical science. In De Magnet, he coined the term electricus, from the Greek word for amber, which was the one substance the ancients knew had this property.
Static electricity.
Exactly. And Gilbert systematically tested hundreds of substances and found that many others, sulfur, wax, glass, also had this property when rubbed. He also made the key discovery that moisture prevented it from working.
And Robert Boyle makes another appearance here.
Boyle proved that this electrical attraction could work across a vacuum. That was huge, because it showed that the effect didn't need air to be transmitted. It was some kind of fundamental force.
And you start to see the invention of devices to study this new force.
Otto von Guericke, who invented the vacuum pump, also invented an early electrostatic generator. And the word electricity itself enters the English language thanks to Thomas Brown in 1646, long before anyone really understood what it was.
It's clear that none of this would have been possible without the tools, the machines of knowledge that allowed for this new level of precision.
They were completely integral. You can't have a mathematical science of the heavens if the calculations take a lifetime to perform by hand.
Which is why the invention of logarithms was such a big deal.
A computational miracle. John Napier's logarithms turned brutally complex multiplication and division problems into simple addition and subtraction. It was an essential tool for people like Kepler.
And we also see the very first steps toward what we would call computers.
The lineage is really clear. It starts with analog devices like the slide rule, invented by William Oughtred in 1622.
And then the first mechanical adding machines.
Blaise Pascal builds his Pascaline in 1642. Then Gottfried Leibniz, the co-inventor of calculus, goes even further and designs a machine that can multiply and divide.
And Leibniz gives us the theoretical foundation for all digital computers.
He refines the binary number system, the ones and zeros. It's incredible to think that at the same time they're mapping the cosmos, they're also mapping the fundamental logic of computation. The need for accuracy was driving all of this innovation.
And beyond calculation, they needed new ways to measure the invisible world around them, like air pressure.
Which brings us to Evangelista Torricelli and the invention of the mercury barometer in 1643. And this came from a very practical problem.
Trying to get water out of mines.
Exactly. Suction pumps could only lift water about 30 feet, and no one knew why. Torricelli realized it was because the weight of the atmosphere was pushing the water up the pipe.
And the barometer was his way of proving it.
He used mercury, which is much denser than water, in a sealed glass tube. The column of mercury only rose to a height that perfectly balanced the weight of the atmosphere, leaving a vacuum at the top of the tube, the first quantitative measurement of air pressure.
And that vacuum itself became a huge subject of study.
Which required the vacuum pump, invented by Otto von Guericke in 1654. And he used it for his most famous public demonstration.
The Magdeburg hemispheres.
One of the great theatrical moments in the history of science. He took two large copper hemispheres, fitted them together to make a sphere, and pumped the air out.
And the air pressure on the outside held them together.
Held them together so tightly that 2 teams of 8 horses couldn't pull them apart. A dramatic, unforgettable proof of the power of the atmosphere and the reality of the vacuum.
In observation, we talked about the telescope, but there was a big split between the two main types.
Refracting telescopes, which used lenses like Galileo's, had a fundamental flaw called chromatic aberration.
The color fringing.
Right. A lens bends different colors of light at slightly different angles, so you can never get a perfectly sharp image. Newton argued this made refractors fundamentally limited.
So his solution was to use mirrors instead of lenses.
Because a mirror reflects all colors of light at the exact same angle. He built the first functional reflecting telescope in 1668, a design that would become the standard for all large astronomical telescopes in the future.
And all this pure science starts to lead directly to the machines that will power the next great shift in history, the Industrial Revolution.
The connection becomes undeniable. The physicist Dennis Papin invents the steam digester, basically a pressure cooker, which is the direct forerunner of the steam engine.
Which leads to the first practical engines for industry.
Thomas Savery patents the first working steam engine in 1698 for pumping water out of mines. Then Thomas Newcomen perfects a much more efficient design. Newcomen's engine really is the machine that kicks off the Industrial Revolution.
And you need better materials to build all these new machines.
Which is where Abraham Darby comes in. He figures out how to use coke, which is derived from coal, instead of charcoal to fuel his blast furnaces. This allows for the mass production of high-quality, cheap iron, the essential raw material of the industrial age.
Before we move on, it's worth noting that the scientific instruments that have survived from this period can be a bit misleading.
That's a really important point of historical context. The instruments you see in museums are often these beautiful, ornate objects made of brass and gold.
commissioned by wealthy patrons.
Exactly. They were status symbols as much as scientific tools.
Yeah.
The actual workhorse instruments, the ones that were used every day in the lab, were probably much simpler, got worn out, broken, and thrown away. They weren't considered collection pieces.
So what we see is a biased sample.
A very biased sample, but the growing demand for accurate instruments for navigation, surveying, and warfare is what created the market and the manufacturing skills that the Industrial Revolution would build upon.
We've called this a revolution all the way through, but that idea of a sudden radical break isn't universally accepted by historians. We should dig into some of those criticisms.
Absolutely. The first major challenge is the continuity thesis. This argument, championed by people like Pierre Duhem, says there was no radical break at all, that the idea of a dark age followed by a sudden revolution is a myth.
So where do they see the new ideas coming from?
They argue that intellectual development flowed more or less continuously from the Middle Ages. They point to the 12th century Renaissance, when all these Greek and Arabic texts were translated, and say that many of the revolutionary ideas were already being debated and developed by medieval scholars. The change was more of the gradual acceleration.
Okay, so that's one view. It was gradual. What's another perspective?
The reassertion thesis, or the Renaissance thesis. This view agrees there was a break with the immediate past, with Aristotle. But it argues the revolution wasn't the creation of new knowledge, but the relearning of older classical ideas that Aristotle had eclipsed.
So again, it's about reviving lost knowledge.
Exactly. They'd point out that Copernicus was reviving the Pythagorean worldview, that Archimedes already had a sophisticated mathematical physics. In this view, the revolution was just an extension of the Renaissance recovery of classical texts.
Then you have a much more recent argument that challenges the whole Eurocentric frame of the story.
The multicultural influence argument put forward by scholars like Arumbala. And his argument is that the key innovations, mathematical realism, the mechanical philosophy, heliocentrism, were not internally generated in Europe. They were the result of Europe absorbing and transforming ideas from other cultures.
What kind of influences are we talking about?
All sorts. He points to the influence of the Islamic scientist Alhazen's work on optics, which was crucial for Kepler, the influence of Chinese mechanical devices, like clocks, on the idea of the universe as a machine, the Hindu-Arabic numeral system itself, which made the new math possible.
So Europe was more of a crucible where all these different ideas were melted down and reformed into something new.
That's the core of it. Bala acknowledges that the final accomplishment, the creation of this new, unified system, belonged to the Europeans like Copernicus and Newton. But he argues the raw materials were multicultural.
Finally, there's the criticism about who gets left out of this story, specifically women.
It's a vital modern perspective. The new institutions of science, the Royal Society, the universities, were almost exclusively male domains. Women were structurally excluded from formal participation.
But that doesn't mean they weren't contributing in other ways.
Of course not. We know women were making advances in areas like herbal medicine, pharmacy, domestic chemistry, but because they weren't part of the formal record-keeping institutions, their contributions are largely invisible to history. Obscured.
It's ironic that the very system being created, with its focus on peer review and formal publication, is what later allowed women scientists to finally get their due.
It is. The foundations were laid for a more objective system, but the doors to that system were closed to half the population at the time.
So, to pull this all together, we called this a seismic shift, and it's clear why. It wasn't just about the big discoveries, as world-changing as they were.
No, the final takeaway has to be about the method. The realization that the natural world must be investigated mechanistically, mathematically, and through rigorous, repeatable experiments.
And that this whole process needed to be institutionalized, made into a system.
That reliance on external observation, on data, is the true legacy. As one historian put it, it was the transition from implicit trust in the internal powers of man's mind to a professed dependence upon external observation.
That dependence on observation is the bedrock of our world. And it was formalized through those 17th century structures like the Royal Society's journal, which gave us priority and peer review.
A system that was born in the age of the printing press and gentlemen's clubs. And today, that system is global, digital, and under unbelievable pressure from the speed of information.
Which brings us to our final provocative thought for you to take away from this. If you were starting a new global scientific institution today, right now,
knowing that the system we have was designed for a world of paper letters and slow communication.
How would you redesign the process of publishing and credentialing science to guarantee integrity, but also to work at the speed and scale of the 21st century? Would you build on those 17th century foundations, or does our digital age require a new revolution, a fundamental break of its own? Something to think about.